I titled my talk today, From Doc's Shoebox to Apollo. Just take an informal survey. How many people find Doc's Shoebox? How many people know what that refers to? Okay, pretty good. It is right outside the door. So, and how many people worked on the Apollo guidance control system here? So a good number. Excellent. My title today, well, is a little bit misleading, although I should also say it's a pleasure to be invited here to Draper Labs, and I won't take it personally that I've been invited to speak on April Fool's Day. And when I realized that I'd be speaking here on April Fool's Day, I had the thought of, well, maybe I should just make the whole talk up from whole cloth and invent it completely. But then I realized how much work that was going to be to make something that was plausible. So I decided to actually give a real talk, but I have embedded in the talk in honor of April Fool's Day, one bald-faced lie. So if you listen carefully, maybe at the end people can detect what that slight fabrication was. And my title of my talk today is a slight bit misleading in that I'm not really going to talk about from Doc's Shoebox to Apollo. Rather, I'm going to tell you the story of Doc's Shoebox and the Mark 14 Sperry Draper gunsight and embed that story in a larger story about the history of feedback control, guidance, and navigation technologies, largely before the Second World War going up through the end of World War II, and then really skip ahead at the end to talk about Apollo, say a little bit about a historical project that we've been working on with the help of Draper Laboratories, and just draw some historical parallels, and then maybe at some point in the future, I'll stand in front of you and give you the talk about Apollo as that project matures, the historical part of it. The story begins in 1916. It actually goes back much further than that and has everything to do with the history of how you aim a gun. But by 1916, the Sperry Gyroscope Company, which is probably quite familiar to a number of you, generated this system for the United States Navy. Sperry, as you'll know, it was founded by the inventor Elmer Sperry in about 1910, 1911, to commercialize his gyro compass, the north-seeking gyro. And you can see that as part of this system right here. This obviously had a whole lot of advantages above magnetic compasses, particularly for navigating submarines at the time, but also for navigating various types of commercial vessels. But one part of the Sperry gyro compass was a gyro repeater. And any of you who work aboard ships will know, still today you find a lot of Sperry gyro compasses aboard ships. And usually the place where the gyro compass is not the place where you want to know what the heading is. So they built a repeater so you could put the gyro compass low in the hull, and then there would be a repeater up in the bridge or at other parts around the ship. And that repeater, which was really a simple kind of DC step-by-step synchronizing device to make two dials come into line, that repeater Sperry realized could be used to transmit all different kinds of data around a ship. And at the time, 1916 is an interesting date. Anybody know what the famous naval event that occurred in 1916 was? Battle of Jutland, right, where the British, who thought they had the best fire control systems in the world, engaged the German fleet in the North Sea at very long ranges and achieved embarrassingly poor performance with the hits of their gunfire. And this created a kind of opening for the Americans to come in and say, actually, we've been novices in this technology, but we're going to try to build our own gunfire systems. And they came to Sperry, and Sperry built them this system, which essentially is mostly based on the simple data transmission of taking a rotating quantity from a target bearing transmitter. There's a telescope on the foretop. They spot the target, and that number, as expressed as an angle, gets transmitted down into the plotting room. There, the basic problem of naval gunfire control is, of course, leading the target. You've got a battleship 10, 20,000 yards away. You've got to figure out where it's going to be at some point in the future. The time of flight for a shell can easily be up to a minute at that point. So you've got to figure out what's the course and speed of your target ship, all correlated from your own target speed, course and speed, extrapolate into the future by some time of flight, run the ballistics backwards, and calculate the angles for the guns to fire in order to lead the target appropriately. And in the first version of this system, that was actually done on paper, graphically. They just plotted all the systems. There was a thing called the battle tracer, which looked not unlike a modern, modern pen plotter. And an officer would sit there with the plot of his own ship and the plot of the target ship and calculate the lead using a kind of slide rule type device. The battle tracer had this unfortunate characteristic that it would run itself off the table in a heavy sea. Other than that, you see in the beginning of this system, the beginnings of this plotting room, which I've expanded out here, but is a room central down in the ship where all the information is brought together. There's a series of calculations made on it based on observations from above, and then the data is sent back out to the turrets to give them commands. And this system was installed in a number of American battleships, mostly after the First World War. By 1940 or so, it had matured quite a bit, although its essential structure remained the same. This is a circa 1940 manual. You can see that radar has been added. I'll say a little bit more about that later. But in the context of the system, radar is but another input. You have optical telescope inputs, you have rangefinders, and suddenly you have radar. And all the data is brought in along central buses. Sperry actually gets kicked out of the business in 1922 for some interesting reasons. General Electric comes in, and there's two new companies that get spawned. One of them both of them actually spin out of Sperry Gyroscope. One is called the Arma Engineering Company. The other is the Ford Instrument Company. And they build what is literally called a computer at the center of this system. This is the Ford Rangekeeper. Also, the original version was built in 1916. Hannibal Ford is a sort of mechanical genius, had worked for Sperry, actually designed the Sperry system I just showed you, spins out his own company, builds this Rangekeeper, all based on this two-ball mechanical integrator, which Ford improves upon a design that had been done originally. The one-ball integrator by Lord Kelvin. The two-ball integrator he patents, incorporates it into this Ford Rangekeeper. And many, many applications of the mechanical integrator come up in later years. In fact, the Redstone rocket had a guidance system built by Ford Instrument, had Ford integrators in it, and there's actually one Ford integrator somewhere in the space shuttle system that remains today. This system worked so well, was basically mature for main battery gunpowder control in about 1930. The accuracy of the fire control calculations were smaller than the natural dispersion of the gun. Therefore, there wasn't a whole lot further to go other than adding radar. And you can see the vast number of variables that were added in. Wind speed, corrections for humidity, corrections for the temperature of the powder, a whole variety of other types of corrections. These devices actually stayed in use on U.S. battleships right up until they were retired in the mid-1990s. When they brought them out of mothballs during the Reagan era, they looked at the fire control computers and decided they were still adequate. And I've been trying to get my hands on one, although it won't quite fit in my basement. But they're beautiful devices. Think about them as sort of refrigerator size with the intricacy of a watch inside and similar levels of precision. Now, in about 1930, the critical problem for naval fire control that comes up is anti-aircraft. Previously, you've basically been going surface target against surface target. That problem gets solved reasonably well, but then you have the introduction of aircraft. And at first, the Navy responds, and the Navy's contractors respond with some fairly interesting but fairly traditional solutions. I'll come back to this picture later on. They try a series of steps and end up with this system, which is introduced in 1937, hence it goes by the name Mark 37, gunfire control system. And it's basically the same thing as the main battery system. They treat the airplane as though it were a battleship, as though it were simply had a z-axis and was flying straight and level, probably coming at you to drop its bombs. You want to hit it before the bombs are dropped, or at least force it to fly away, or at least force it to take evasive action to screw up its own sighting mechanisms for its gun sight. There's an element of visual perception I'll show you inside this box in a moment. This piece is up on the top of the ship. It's stabilized by a very large barbette. It has a tracking servo that will actually allow it to track the targets semi-automatically in rate control. Again, the data is brought into what is now called a computer. Like most historians of technology and historians of computing think the word computer was only applied to human beings and not applied to actual calculating equipment until after the Second World War. In the world of fire control, you find the word computer being used right up into back into the 1920s. 1920s. Into the Mark I computer, a stable element built by Armor Engineering Corporation is really a kind of proto-inertial platform. It keeps a horizontal and vertical reference, which was previously done by having sailors train telescopes on the horizon. So this particular system becomes fairly integrated. Then it has an automatic servo control to move the gun automatically. And you find they're quite popular on American warships all through the Second World War. Inside, this is the large optical rangefinder coming up. You can see the baseline for the rangefinder, several different operators. There's one pointer and one trainer who control the rotation and the elevation of the actual target tracking. One officer in charge of the whole thing an officer to control firing star shells, all connected by audio networks. And you're beginning to see this pattern of optical inputs, mechanical outputs from the users, and then connections by various kinds of audio and data transmission systems. And you begin to see many of the issues that later come up with computer networking are beginning to come up in these communication networks on warships. The external feature of this system looked like something like this. This is among the most popular icons on World War II era battleships from the United States. You can still see them on the USS Massachusetts down in Fall River, on the Missouri in Pearl Harbor. One of the most common sights on an American warship, right from destroyers up through the battleships. Interestingly, it was hailed as the first anti-aircraft director specifically designed to incorporate radar, which was added. This is a Bell Labs radar from about 1942. I looked at the drawings and tried to figure out exactly what they meant, and it turned out what they meant by that was that the top of the barbette was flat so you could mount the antenna on it. And that's actually rather revealing about what people thought about what today we would call systems integration at the time. They weren't thinking very much about data flows. They weren't thinking very much about electronics or interfaces at the guidance level, but rather people were still in a very mechanical mindset. Integrating radar meant mounting the thing on the top of the turret. Now that soon proved to be a problem because this system had problems with stability in its servos. As it would try to track a target, as it tried to track the target, it would move its own servo to keep tracking the target, and there became an instability in the relationship between the automatic semi-aided tracking algorithm, which was done inside an analog computer, and the servo that actually turned the turret. And this system basically is unstable at the beginning of the Second World War, and the Navy really has no way to fix that problem. And I'll come back to that in a moment. At the same time, the Army during the 30s is also dealing with the anti-aircraft problem. This is a plot from 1930 of the Army's vision of how you shoot an airplane out of the sky and what the numbers involved were. You can see that this is only for about 20,000 feet. You're talking about 30-second time of flight, and for a, let's see, how does this work? 240 plane, well, for a plane traveling 100 miles an hour, you've got one set of problems. Then for a plane traveling 240 miles an hour over the course of a minute, you have hundreds and hundreds of yards you've got to calculate the lead for. And of course, altitude and speed of bombing aircraft are going up rather rapidly during the 1930s. So this is an extremely difficult problem. Again, Sperry gyroscope comes back in. They get basically booted out of the Army system. They get booted out of the Navy in 1922. By 1925, they're using the same technology working for the Army. They developed this system in about 1930. It's the first of a series of systems they build over the course of that decade in research, and then they have a few operational at the beginning of the war. It's an interesting system because, for one thing, it has three inputs. That's elevation, range, and azimuth of the target. Yet it requires 9 operators to run it. And you can see from a kind of human factors point of view, this is a fairly comical situation because the actual tracking head, this whole top part of the unit, would rotate as they tracked the aircraft. The telescopes were fixed on it. And I can only imagine that these guys here would have had to shuffle around as the thing was turning. Not an ideal situation. fairly typical of the level of kind of grasping for solutions that we're dealing with the anti-aircraft problem. Now, why is that? A very interesting reason. Here are the three inputs. Each one has its own operator operating that particular device. Then they come into this calculation unit, and these men operate, Sperry calls them human servo mechanisms. In another parlance, you might call them impedance amplifiers. Every time the data comes from one stage to the next, it comes out to what they call a follow-the-pointer operation. And this is literally, all he does is look at a dial that has two needles on it. One of them moves around, and the operator moves the crank to keep the other needle in line. And of course, today you'd say, well, why don't you do that with a servo mechanism? And at the time, they really didn't have the ability to make servos that would be both powerful and precise enough to move those kinds of to do that kind of operation. There were also issues with the kind of subconscious filtering that they wanted the human operators to do, who could see if there was data that was patently absurd, and there was a kind of unconscious smoothing that the operators would perform. But it's very interesting that connecting the stages in a calculation system in the 1930s was a job that was done by a human being, and that's a critical point that comes up later as well. This slide is not extremely clear, but it gives you a sense for the mechanical layout of this system. One of the things that's very interesting in looking at that history is when they start to move from making purely mechanical representations, i.e. mechanical drawings, into these kind of hybrid representations, which are sort of schematics but still fairly mechanical, and then as they move to purely information flow-based diagrams, shows you a lot about how the engineers are thinking. Also here you see this particular device, which they called a ballistic cam. Right? This device has to do both the prediction, the overall system has to do the prediction of the future position of the target, but it also has to do the ballistics, and ballistics is more or less of a lookup table operation. Traditionally, artillerymen would look ballistics up in firing tables, big lists of numbers. And what Sperry did was they mechanized the firing tables by putting them into these three-dimensional cams. And it's a very interesting story as well. They would put three of them actually on a single shaft, and using a pin that would follow along, the shaft would rotate, that would be one variable, and then the pin would move longitudinally along the cam, and that would be the second variable. And so you could store tables as functions of two variables, and you could store three tables at a time on one cam. And if you look at the way that they manufactured these systems, it actually began to resemble numerically controlled machining without actually having a computer in the loop. So you start with a ballistics table. It's actually over there on the left. They would drill a whole series of holes in a cylinder, very precisely calibrated, one for each data point. And then a skilled machinist, you can actually see the remnants of the holes here, would smooth between the holes. And in the effect, he's doing a digital to analog conversion from a digital firing table into an analog cam, and also smoothing the data in between. Now, the manufacturing of these computers turned out to be a major issue. And in 1940, the Army is extremely concerned about the anti-aircraft problem. They're extremely concerned about shooting down high-altitude bombers. And they come to Sperry and they say, we want you to build these things in as high a capacity as you can. And the problem is they're directly dependent on very highly skilled machinists. The accuracy of the mechanisms has everything to do with the precision of the machining and the skill of the machinists. And these are people who were in very short supply during the Second World War. So Sperry turned to the Ford Motor Company to produce these things. This is a very interesting photo, because this guy here is named Charles Sorensen, and he was Henry Ford's chief engineer way, way back in the early days and all the way through the history of the Ford Motor Company before the Second World War. He designed all the actual layouts for the assembly lines at the Highland Park plant when they started building the Model Ts in 1914, and had this mindset of, in his words, anything we can think about, we can mass produce. So they came to this problem and said, oh, no problem. You want a large number of these computers? We can make them for you. And Sperry, slightly sleepishly, turned over the production of these things to the Ford Motor Company. Ford brings that device right into the Highland Park plant, literally onto the same shop floor where they originally manufactured the Model T. Their philosophy, of course, worked extremely well with aircraft during the Second World War. They built a plant called Willow Run in Michigan, where they manufactured B-24s by the tens of thousands, I think. They'll try that with these mechanical computers. Right in the same place where they perfected the Model T assembly line, they start manufacturing these computers and completely fall on their face and can't produce them at all. It takes them twice the original contract period to deliver half of the original number of machines. And this is in 1940, 1941, when the Army is extremely nervous and extremely concerned about anti-aircraft. So mechanical computers for the use of anti-aircraft calculation actually reach their limit in manufacturing before they reach their limit in precision. Now, Sperry is an interesting story, very connected to Draper, as some of you will know. They're producing many other devices. Here's their mechanical gunfire control computer, but they're also making searchlights. They're also making, this is the original gyro compass, listening equipment for detecting aircraft, automatic pilots that link their gyro compass through a feedback loop to control ships on stable courses, a variety of other instruments, and they're also getting into the aviation business with artificial horizon is a Sperry product, turn indicator is a Sperry product, and an automatic pilot, which they introduced in the early 1930s. This is Wiley Post, who's a very interesting character. He's sort of a poor man's Charles Lindbergh. He flies around the world with a co-pilot in 1930, the first flight around the world. In 1933, he does exactly the same flight, but he does it by himself, and he does it by replacing his navigator with a Sperry automatic pilot. And actually, Post's plane, the Winnie Mae, is right front and center today in the National Air and Space Museum, and the prototype Sperry automatic pilot that he used is also, you can see it at the Smithsonian. And so Sperry has a lot of other things going on, and they're getting very big in aviation. Nearly every American warplane produced during the Second World War has Sperry instruments in it. And they're also, like the Navy, beginning to realize that there's more going on to this automation business than their kind of basically mechanically trained engineers can really handle when they get into the more complicated control loops. One other piece of the story before the Second World War happens at MIT. Vannevar Bush and the differential analyzer. Many of you may be familiar with this story. The differential analyzer is also, like the Ford Rangekeeper, a mechanical analog computer. It's slightly more modular, but it's based on integrators, just like the Ford integrator is. They don't actually use Ford integrators. They use a different kind for a separate reason. The Army is definitely interested in it, as you can see in this picture, for the purposes of calculating ballistic tables. And Bush has this idea about, well, if we can build basic, simple, interchangeable mechanical units, then we can combine those to model almost any kind of system that we can think of. The differential analyzer itself is basically a real-time graphical control computer. And what I like about this picture, it shows you that the differential analyzer had literally a graphical user interface. This is how you got data into the computer. It was originally plotted on graphs, and then an operator would sit there. You can see he's got a little magnifying glass to improve his accuracy, and just draw a pointer across it, almost like a reverse plotter or a digitizing table today, and that's how the data would enter into the computer, and then the computer would plot its outputs as graphs. Now, Bush's students take this basic idea quite a bit further, and this is Harold Hazen, who later joins the faculty at MIT, and he has an important realization while he's working on the differential analyzer. That is to say, in order to make the blocks of the computer truly interchangeable, you need some kind of impedance amplifier between each stage. That is, if you just keep adding mechanical units, you're going to load the thing down and lose accuracy due to friction. Sperry, remember, solves that problem with human servo mechanisms. At MIT, they're trying to solve that problem with servo mechanisms, automatic, electrical, or in some cases hydraulic units that will just take a mechanical input and follow it. And Hazen, while he's working on his PhD thesis, has two important realizations. First of all, those servo mechanisms basically work like amplifiers, and the fundamental thing that they do is take a signal, a mechanical signal in this case, at a small power level, amplify it to a larger power level. And secondly, that the feedback dynamics of what goes on in those servo mechanisms is similar to the feedback dynamics that go on in an automatic pilot for an aircraft, in a thermostat, in all different kinds of regulators that have been going at the time. He writes a paper in 1934 called Theory of Servo Mechanisms, really the first paper that takes the problem of feedback as a whole and tries to put it on a theoretical foundation. And what it also does is it moves there are a lot of people at the time worrying about speed regulators, pressure regulators, all different kinds of regulators, but almost all those regulators are steady state devices. And Hazen brings that into the world of dynamics and says, hey, we don't just care about how the thing settles out after you tweak it a little bit, we care about dynamic response. And the speed of response is important. He worries a lot about transients. You can see him here. He's even working on a device to track a transient from a graph plotted on paper. And Hazen introduces this problem of transient behavior in servo mechanisms. Very interesting to the aviation people because aircraft are increasingly not working like sort of steady regulators in the way that they'd been thought of, and there's a whole other host of problems that are also being thought about that way. Now, another Bush student is Gordon Brown, who sort of takes over from Hazen in the late 1930s. And in 1939, the Navy realizes that they're having problems with this Mark 37 anti-aircraft director. They just don't understand how the feedback is working well enough to stabilize the thing, and it's having problem in its servo loop. So they take 4 young officers, lieutenants, who were fire control officers. And at this time, recall that it's the years before aviation rises to the top of the naval hierarchy. And the people who really ran the Navy were the battleship admirals, who got a lot of bad press during the Second World War. They were known as the Gun Club. Very small, very cliquey group. And of the battleship group, of the battleship officers, it was the fire control officers who were the top of the heap. Partly because these were the guys who aimed the guns, fired the guns, and it was considered a very difficult, abstract, mathematical discipline. They take 4 of these young men, send them to MIT to get their master's degrees during the academic year 1939-1940. Those 4 take a number of different remedial math classes because they're not quite ready for what MIT throws at them. But there are 2 classes that really excite their interest. One of them is Gordon Brown's class, the first class ever taught at a university on servo mechanisms and servo mechanism theory. And the second one is Doc Draper's course on aviation instruments. And Draper agrees to sort of bypass the aviation instrument course he usually teaches and teach these 4 officers all about the basic physics of gyroscopes, and then to tell the Navy that he really taught them about aviation instruments. Of these 4, 2 of them write their master's thesis on this problem of stabilizing the large gun turret with a very large servo. They use Hazen's theory of amplifiers to study how to amplify a very small signal from a fire control computer into a very large signal to move a turret. 2 of the other students say, hey, you know, we've been learning from Draper about these gyroscopic turn indicators that he's been making. And when you think about the anti-aircraft problem, it really comes down to calculating the lead, and you basically want to differentiate the velocity of the target in order to calculate the lead. Why can't we use one of these turn indicators that Draper's using and build it into a gunsight and think about using it as a gunsight? Well, they tell this idea to Bush, who's their advisor, and Bush says, oh, why don't you go talk to Draper? So they go talk to Draper and they tell him about it, and they had been taking his course, and they say, as soon as we told Doc Draper about this idea, he froze, and then he shut up like a clam and wouldn't tell us anything more. So there was something going on back there that they were not privy to. Both of their master's theses, by the way, were classified until the 1970s. So now it's the spring of 1940. These 4 officers are just graduating from MIT with their master's degrees. Right about that spring, the Battle of Britain is raging. The Nazis are racing across Europe. France falls to the Nazis in June of 1940. And Vannevar Bush, down in Washington now, organizes the National Defense Research Committee. And I'm sure you've read about this group. They're the ones who spawned the Manhattan Project. They're the ones who sponsor the radiation lab here at MIT. And they also develop a group dedicated to fire control. This is one version of that committee. It's led by Warren Weaver, who's the head of the Rockefeller Foundation. It's an interesting background to that story as well. Preston Bassett, president of Sperry Gyroscope. Harold Hazen, who I mentioned before. Sam Caldwell, another one of Bush's students. Thornton Fry, head of mathematics at Bell Labs. Yvonne Getting, some of you may be familiar with. He at the time is with the radiation laboratory, young MIT physicist. George Stibitz built some of the first telephone relay computers at Bell Labs. George Philbrick, any of you familiar with the old days of analog computing will recognize Philbrick's name. Carl Wilds, also from MIT. This group lets 80 contracts during the course of the Second World War. Every single American pioneer in digital computing does one of those contracts. Norbert Wiener, Jay Forrester, Eckert and Malkley at Penn, Adin Alsop at Iowa State have a major influence on the way that computing develops, all focusing on this anti-aircraft problem, and this is the way they formulate the problem in the 1940s. Western Electric, of course, is the manufacturing arm of Bell Labs. Bell Labs builds an electrical version of basically the Sperry mechanical anti-aircraft computer. No innovations in algorithms, no innovations in computations. They just take the basic algorithm, they implement it with electronic devices. In the process, they invent what is now known as the operational amplifier, using feedback amplifiers to do basic mathematical operations. And it's not even as accurate, the machine in the end, as the Sperry device was. But it's built by Western Electric, which has a lot of extra capacity. You don't need precision machinists to manufacture this thing. You can manufacture it with people who know how to do wiring. And there are a lot of those people around. The telephone company is underutilized early in the war. So a very interesting story about how the shift from mechanical to electronics and computing is driven as much by manufacturing as it is by accuracy or speed. Or the way they put it, speed and accuracy are terms that apply to the workers, not just to the calculations. One of these projects, is a separate story, I wish I could spend more time on it, is this radar called the SCR 584, which is designed at the radiation lab. It's the first radar where the servos that move the antenna are coupled to the actual receiving the received echo from the tracking of the target, and it will actually follow the target automatically. And remember, this is exactly the kind of problem that the Bureau of Ordnance was not able to solve with its anti-aircraft computers before the war. The people at the radiation lab basically solved it successfully. Very interesting group of people work on that project. And they couple that system to the Bell Labs mechanical computer during the 40s. Again, very interesting in terms of system integration. You have two completely separate systems. One is doing the calculation, one is doing the tracking. They were not designed really with a whole lot of talk between them except for the actual raw interfaces. They were lucky that it worked, but they began to see that this was not the way to design an integrated system. This system, like all the prior systems in fire control, again, they're thinking about the problem as a bomber's coming at you, it's flying straight and level, you track the linear flight, you predict it into the future, and you shoot the thing down. And in the 1930s, that was a reasonable assumption. Of course, it doesn't take long for enemy pilots to realize that if you fly straight and level, you're going to get shot down. The systems don't prove very successful against human bomber pilots. They prove incredibly successful against these V-1 buzz bombs, which are these sort of early cruise missiles that begin coming across the channel right after D-Day in 1944. They fly absolutely straight and level. They're small, they're fast, they fly low, they're very difficult to hit manually, but they will not take evasive action no matter how much you fire at them. And so the prediction algorithms work incredibly well on this particular device. And it's a very interesting story you see being played out in the southern part of England during late 1944, where you have essentially an automated tracking system versus an automated enemy. And some of the early, what today we would call a cybernetic battlefield, begins to emerge in this brief episode. This is an amazing shot, actually, of that automated system shooting down a V-1. And you can see, you know the thing is being shot down instead of going down of its own accord, because when they would land to crash and explode, intentionally it was because the fuel would run out and you wouldn't see the trail anymore. And here are the shell explosions from that tracking system. And you can see that they continue to track the trajectory of the flight after the thing has been shot down. A big success with the Army version of the system built by Bell Labs and GE and the Radiation Lab in Europe. The situation in the Pacific, however, looks quite different during the Second World War. Again, now we're dealing back to the Navy, who's had these very sophisticated systems before the Second World War, but they did so without a very great sensitivity to the changing nature of the threat. Of course, Pearl Harbor in 1941 it's not lost on the Navy that it pits airplanes against battleships, and most of the battleships end up at the bottom when that happens. One of those battleships is the USS Utah, not a particularly new one, not a particularly interesting one to a lot of naval historians, except for one fact about it. It was the oldest, actually, battleship in the fleet up until Pearl Harbor. The man who had been captain of that battleship had been taking it out, and what they had done with it was convert it to an anti-aircraft training school. And this guy, Blandy, was a member of the gun club, and he gets assigned to the oldest ship in the fleet, and it's considered a kind of backwater assignment. He spends most of 1941 taking out a bunch of new sailors, training them how to use the various anti-aircraft control technologies that they have, sort of one of each kind mounted on the Utah. And also, then they also used to train the bomber pilots, and they're sitting there on the deck of this thing being dropped, having water and wooden bombs dropped on the deck of the ship. Blandy realizes that everything the Navy has to combat both close-in torpedo attacks and dive bomber attacks just doesn't work at all. All of these systems that have been designed by basically the surface fire control companies, Ford and Arma, are designed to treat aircraft more or less like battleships. And the tactics that are evolving with new aircraft, even in the American Navy, don't follow those straight and level, predictable flight paths at all. In fact, most of those systems work by converting the observations, which are basically taken in polar coordinates, into Cartesian coordinates, doing the prediction in a Cartesian system inside the machine, and then converting back into polar. That works reasonably well if you're firing at a battleship that's 10,000 yards away that's moving on a course that's sort of oblique to your own course. It doesn't work very well when you've got things coming in at you along more radial lines, which is how the war begins to shape out. Blandy writes a very scathing memorandum to the Bureau of Ordnance in 1939 with a plan for what they should do about anti-aircraft fire control. They bring him to Washington in 1940. 1941, the head of the Bureau of Ordnance, Furlong, comes out and he becomes the head of the salvage at Pearl Harbor. Blandy is put in the head of the Bureau of Ordnance. He's the youngest line admiral in the Navy. He's promoted above 55 senior officers to run the Bureau of Ordnance. So the Navy is recognizing fairly belatedly that anti-aircraft is the major problem that they face in defending their ships. Blandy's anti-aircraft program is well illustrated by this illustration, which comes directly from one of his proposals, which is, this is the armament that's originally proposed for the South Dakota, which was built during the Second World War. You can see there's about 10 or 12 anti-aircraft guns on it. By the time the thing is actually built, it's completely studded with anti-aircraft guns, both the 20 millimeter Oerlikon, which is a smaller one, and the 40 millimeter Bofors. Interesting, too, this is a Swiss gun. This one is Swedish. They're both also used by the Germans and by the British at the time. Much better than anything the Americans have to offer. And if you go visit any of the World War II battleship museums, again, Fall River, though I think the New Jersey is down in Philadelphia, certainly the Missouri down in Pearl Harbor, you'll see there's basically an anti-aircraft gun. Anywhere on the deck, there's a blank space. They pop them on top of the turrets. They stick them all around the outside. They're completely obsessed with defending these battleships against aircraft. What Draper had been working on when the two Navy students came to him was this idea he had called Doc's Shoebox. The British merchant marine had actually come to him and said, is there any way you can help us defending our merchant ships against Nazi air attack as they're going up and down in the North Sea? Draper's not working for the Army. He adapts he's not working for the Navy. He adapts what had been his gyroscopic turn indicator into what he considers a tank sight. And it basically works in one dimension. And again, the tank problem is not unlike the battleship problem, but Draper solves it in polar coordinates and not in Cartesian coordinates, and it makes the mechanisms much, much simpler. The whole thing can be much smaller. Of course, this device right here is right outside the door there in the glass case. And this is the problem that Draper's working on. And you can see, originally he even conceives of it really only as solving it in one dimension. This early vision of it, which is probably 1942, he's not worrying about dive bomb attacks or close-in attacks. He's still thinking about the kind of oblique course problem. the 4 Navy students who had been working here all go back into the Navy at the end of 1940. 2 of them end up working for Blandy at his new anti-aircraft division. One of them, a guy named Horatio Rivero, all 4 of those guys became admirals, by the way. One of them, Horatio Rivero, ends up at the head of the radar desk, and they sort of say, hey, what's this radar stuff good for? And another one ends up working on the anti-aircraft desk. And Rivero goes to his boss and says, you have to go talk to Draper, because Draper's been working on this thing. The guy knows how to make things. You really want to go there and have a look and think about these small gyroscopic gun sights rather than these enormous, complicated Cartesian computers that they'd been using. And Draper's idea is turned into the Sperry-Draper Mark 14 gun sight. Interesting story between Sperry and Draper. Sperry had been funding a lot of Draper's work during the 1930s, very similar to the kinds of industrial research contracts we have on campus today. Much of the work that was done in Draper's lab, the patents were owned by Sperry. Sperry had manufactured a series of vibration measuring devices and knock indicators for aircraft based on Draper's designs. Very close relationship already with Sperry. So it's fairly natural that Sperry and Draper work together in this way. And in effect, all he's really doing is taking one of these aircraft instruments and putting it inside a box on top of a gun. Here's the basic principle of operation. It's called a disturbed line of sight device. And basically, if the gunner follows the target, the device itself calculates based on, you dial in the range. You can see this guy here actually is dialing in the range by hand, something that the fire control professionals in the Navy look down on because it's very kind of ad hoc, not nearly precise enough. Of course, if he's a kamikaze and he's flying straight at you, you can just set the range at a couple hundred meters and he'll pass through that range at some point. And then the sight, the sight is actually designed specifically to offset, and all the gunner has to do is keep the plane in the center of the sight, and it'll force him to calculate the right lead with his hands. Here's the actual thing in operation. This is actually also on the 20 millimeter Oerlikon gun. And you can see the muscle power of the human is still doing all the working. In fact, in some ways, there's still a human servo mechanism in the loop, but the gunner is, in a sense, being visually fooled into leading the target. Sperry makes 85,000 of these things during the Second World War. I was very fortunate. I actually bought one off eBay for $100 last year. The guy who sold it to me had no idea what it was. It was still in its original box and had its original inspection tag on it from 1942, and as near as I could tell, had never been removed, never been used. Except for some peeling paint, it's basically in perfect condition. And this is the basic principle of operation. There are 2 gyroscopes in it. Again, there's one of them sitting right outside the door here. You can look in and see for yourself. One in azimuth, one in elevation. The precession of the gyros as they move essentially differentiates the angular rates that the gunner is moving. There are 2 springs that constrain the gyros, and you adjust the tension on the springs to reflect the range. That's the proportion that the springs, the gyros deflect in proportion to the range, and then it's connected by a very elegant, lovely set of linkages up into the mirror. One of the great things about this device was that all it required was compressed air to run the gyros and a little 12-volt supply to power the light inside the reticule. So you could bolt them anywhere on the ship. You didn't need a whole complicated set of data transmitters and complicated set of interfaces like you did with the larger, more centralized system. So you're moving fire control out from the centralized part of the ship into these kind of distributed semi-autonomous units. It also works in this way that had been very characteristic of both Draper's work and Hazen's work at MIT, focuses on dynamics. It's not concerned with static operation. It's not concerned with settling on a particular solution, but basically assuming that the inputs and the outputs are always changing. By the way, one of the interesting stories about this, too, is that at Sperry at the time, the lawyer who does all the contract work with MIT to get this thing into production is a young aviation lawyer named James Webb. And, of course, 20 years ago, Webb is the administrator at NASA, comes right back to Draper when he needs a guidance system for the Apollo program. Here's a shot in the Pacific in the late part of the war. You can see these Sperry-Draper sights just lined up with these 20 millimeter guns. How well they actually work to shoot down aircraft is another question. One of the common things was, well, basically they were kind of alarms. If you were down below and you heard the 20 millimeters going off, that meant you head for the deck because something was coming in close. Whether they actually shut anything down is more of a question. Another version of the device could be used to operate a remote gun mount. This is actually one that's today on the USS Massachusetts. You can go down there and move it around. This is the Mark 15 site. Actually, it's Mark 52 site. There was a smaller one that was the 15. A Mark 51 site had a larger telescope to work in range, and it was instrumented with cell SINs that could then transmit to a servo. So here you see, back to this shot, it's actually a rather famous shot of the Missouri being attacked by a kamikaze. And you can see, here's the fire control device being operated by a gunner, and here's the actual 40 millimeter quad mount that's being moved by the servos. Same thing here, it's not as clear. There's one of these devices up here moving this mount, another 40 millimeter mount, and yet another one here moving this 5-inch mount. And here again, you've got this idea that Hazen brought up of the servo as an amplifier. You've got these little devices being controlled by fairly small angular motions and muscular motions and gyroscopic sensing of the motion in the sight, amplified with these very large hydraulic servos, also designed at MIT actually, to move these guns automatically. And combined with the proximity shell, the proximity fuse, these things do a reasonably good job late in the war of defending against the kamikazes. But again, the kamikazes, when they come up, break all the rules of pre-war fire control. They don't fly in Cartesian trajectories. They're not trying to drop a bomb on you. They don't really care if they get away. They've got to be physically stopped before they come in. So it's interesting to think about the comparison of the Pacific Navy situation with the Army situation in on land in Europe, where you've got automated systems from one culture versus automated systems from another culture. When you're facing the Germans, you're facing an autopilot inside a guided missile. When you're facing the Japanese, you're facing a human pilot inside a human guided missile. And the way that the defensive systems sort of have to change their assumptions, and they're progressively undermined and then readapted to these new threats. And usually the things that worked are not things that people predicted would work. Just to review then, there's a series of other projects that go on these same problems during the war. This is a project that's done at the radiation lab, where they take these two separate radar control units and really try to bring them together into an integrated system. It's not really ready until after the war, but it does serve in the Navy till the 1970s. People like Claude Shannon work on the problems of smoothing in fire control. His information theory, which is published in 1948, people usually attribute a lot of the influence to his work on cryptography, which is true, but he had also done quite a lot of work on the fire control problem and various issues of smoothing and prediction in mechanical computing devices. Also at the Servo Mechanisms Laboratory, they're combining the theory of feedback amplifiers, which developed by people like Boda and Nyquist and Harold Black at Bell Labs during the 1930s, with these larger, more high-power hydraulic and electrical servos. And of course, they end up developing the Whirlwind computer. Interesting story in itself. Transmogrifies in the 50s into the SAGE air defense system, which spawns all these local institutions like Lincoln Labs and MITRE Corporation. And you can see here that in many ways the operators at these SAGE consoles are not so different from the original Sperry operators. They're taking data on a visual chart, they're observing the data, they're making various kinds of modifications, filtering, decisions about the data, and then outputting some kind of input back into the system. And there's been some very good work done lately about how this system, particularly, and many of the people who worked on those projects, you can track that through only a few academic generations fairly cleanly right down into graphical user interfaces and the kinds of mice and the way we interact with computers today, the DARPA programs of the 1960s. Norbert Wiener's work on cybernetics, of course, if you recall that book, the first chapter in that book is all about anti-aircraft fire control and the prediction problems and how you predict statistically human-machine interface issues. So now I'll jump forward to Apollo and just draw a few parallels and lay out some of the overall overall story about why the Apollo guidance and navigation system is actually quite interesting when you put it in this broader context. It's interesting in and of itself as well, but most historians of computing have previously looked at the Apollo guidance computer and said, oh, it wasn't that innovative architecturally, algorithmically, compared to the other computers that were being built at the time, and they basically ignore it. And I think that's the wrong way to look at it, because it doesn't consider these other kinds of threads and how they relate to other things. Here already you can see in the alignment of the system you've got a visual input, you've got the same kind of mechanical output. The basic layout of the system drew a lot from early work, not just in the Mark 14, obviously. There's 25 years in there that I'm ignoring and skipping over, but the human-machine interface issues that came up during Apollo were not that dissimilar. Here's another sketch. Some of you, of course, I'm sure, are quite familiar with this imagery of the lunar lander and the optical alignment, human-machine interface, the role of the human being as an interpreter of the data, as a coupled link in an information system. This is a great shot, comparative study of what level of automation would be appropriate for the Apollo capsule. The one on the left is no automation. The astronauts are too busy. The one on the right is the full automation. The astronauts are just sleeping and smoking cigars. And when digital computing became introduced into this problem, and it's not unlike the problem that people like Wiley Post faced about how much of the thing is being done by the machine, how much by the human. We asked Eldon Hall, who headed that project or part of the project for Draper here, could your team have built a computer to land on the moon without the astronauts at all? And he said, well, at first we said yes, we didn't need the astronauts at all. Then we decided we needed the astronauts to calibrate the system and do the star sightings. We couldn't actually do the star sightings fully automatically. I said, okay, so the astronauts are calibrators, but actually in NASA's version of the story, and in the goals of the system being to send a human to Earth, to the moon, and bring them safely back to Earth, the humans had to be much more involved. So we're interested in how the guidance and navigation system evolved as this kind of story about what's the appropriate role for the human operator, what can you rely on them for, what are they unreliable for. Lots of interesting stuff there. Also simulation, Apollo in general is one of the very early heavy users of simulation as a real aid in engineering development. That's a story that's progressing through the Second World War as well. People like George Philbrick are very involved in building analog computers and analog simulations. The X-15 program, which Neil Armstrong came from, was one of the first that really used simulations in a heavy way for pilot training during aircraft development. And of course, today, lots of people talk about we live in a world of simulation. There's a lot of public rhetoric and public discourse about virtual reality, and I think you can see many of the early phenomena that characterize that part of today's world going on during these programs back in the 50s and 60s. Manufacturing, again, of course you know that the Apollo guidance computer was this, not the first, but very significant early use of integrated circuits, especially on a large-scale mission-critical application. This woman actually was an employee before she worked for Raytheon of the Waltham Watch Company, and many of the workers who actually assembled the stuff had worked for these older New England industries, and so it's not just a case of digital computing being the new that kind of comes in and erases the entire old world, which is usually how the history of computing is told, but very much building on, again, skills in manufacturing. Who do you have? How can you build them? Clearly, a lot of this wiring work done in core memory modules, not so different from textile work, and New England has a lot of unemployed textile workers after the Second World War. Other very interesting stuff, of course, about integrated circuits. So what we've been doing, and I'll just end on this note, we have a project that's funded by the Dibner Institute and the Sloan Foundation, and we've been working closely with Catherine Grancelli and Linda Petkunis at the library here at Draper, people like Eldon Hall, and we're putting together a web-based history project where we've been posting a lot of the original documents, conducting interviews locally, but also using the web as a way to try to collect oral histories and reminiscences and discussion from all over the country or all over the world. Now, when we've been doing it, working with people who are local here, it's easy. We tend to get them in a room together. But the idea is to segue the personal interviews with web-based interviews, and we can expand the scope of collecting information, both from the astronauts, from the engineers, people at NASA who are administering the program, even factory workers, technicians, people who are involved with the Apollo system in one way or another. Sandy Brown, who's here in the audience, is a graduate student working with me at MIT, has been doing a lot of this work. We've been getting people together for a series of conferences. I'm sure you recognize a number of these faces. And talking through a lot of the various engineering management issues. We did one on the software, management of the software project, where people went after they left the project, how the project's know-how kind of found its way into the New England economy and the economy of new software and hardware companies, how the project was managed, how people reacted to the project. And we transcribe all of these conferences, run them by the participants who edit them and include or exclude things, and then post them on the web that then other people can participate in the discussion. So I'll end with just two pieces of information. The first is the website that actually is running that project. We encourage and ask all of you to come log in, especially if you were involved in the project, participate in the discussions, add your own versions. You can upload your own documents. You can scan documents. You can send us documents. We'll upload them. Most of the Apollo stuff is in the public domain, so it's pretty straightforward from a copyright point of view. Or just feel free to browse around, and there's a lot of original material on there. We also have another postdoc, Slava Gorovich, is working on it. He's doing the whole Soviet part of the problem. He's a Russian historian of science and technology, and he's looking at the comparative computing and guidance solutions that were developed in the Soviet Union, both for the Soviet Moon project and other Soviet space computing projects. And then I'll just put in a plug for my book, which has about 50 times more information than I've been able to convey to you here, and it'll be out from Johns Hopkins in 2002. That only goes up through 1945, and more or less ends with Norbert Wiener and Cybernetics and starts in 1916. And in a sense, the second volume of it will be about Apollo. Hopefully we'll be out in another year or two, and maybe I'll come back and speak to you about it at that point. So thank you. The Soviet approach was more automated than the American approach. And there's actually a wonderful, this is the kind of source that historians get really excited about when you find there's a letter from several of the Soviet cosmonauts to Brezhnev basically saying, you know, we're heroic astronauts, we're heroic pilots, we're risking our lives. You know, why are you letting these pointy-headed engineers do all the guidance system, and we want to be more involved in the process. So that's how it seems to be emerging. But there's a lot of really interesting stuff about the Soviet project regarding the eventual privatization and commercialization of the different processes. And in the United States, during Apollo, there was some contesting of the awarding of the contract to Draper, but once it was awarded, it was basically done here. And there wasn't a lot of competition in that sense, whereas the Soviet project there were more like 3 or 4 competing projects, and they were all positioning to use the level of automation in one way or another for their own commercial goals. And that continues to this day, and many of the people who had headed those projects in the 60s were very involved in the publicizing of the various design bureaus into privatization. So we're just, there is a Soviet section of the site, and we're just beginning to work through it. And a lot of the sources are in Russian, so Slava spends a lot of his time translating. But we're hoping by the end of the year to have the Soviet engineers who worked on it, if we can get them computers, logging in and discussing, but mostly in Russian, and then we'll translate part of it as we can.
Look into Japanese technology during World War II?
I didn't actually. I've seen some of it in that some of it is in the U.S. Navy files about stuff that they went in and captured after the war, but I haven't generally focused on that. My sense is that, like the German technology, it's much more heavily focused on optics and concentrating on using the best optics possible. There's a story at Savo Island in Guadalcanal in 1942 where the Americans were on patrol, basically, and they said, oh, we'll see the Japanese coming. We have radar. We can see them at night at 2,000 yards. Of course, the Japanese had excellent optics, and they selected their rangefinder operators for their night vision so they could see them at 5,000 yards. And but I haven't looked very much comparatively at that. This project was mostly American-focused, a little bit British, and even that was rather large and unwieldy. So.
Did the Norden bomb site have any MIT or?
Good question. No, it didn't, not that I know of. But Norden himself was just like Hannibal Ford. He was a Sperry Company employee who spun out of the Sperry Gyroscope Company in the 1920s. And it's a very interesting story about government contracting because both the Ford Instrument Company and Arma Engineering and Norden were private contractors that sold exclusively to the Bureau of Ordnance. So in a sense, before you had large government labs, or in a sense before you had places like Draper, when the Navy needed new technology, it would just form its own company or allow an entrepreneur to form a company and basically trade not quite guaranteed, but very highly favored contracts in exchange for absolute total secrecy and exclusive rights. And that's one of the reasons they booted the Sperry Gyroscope Company out, was that Sperry had this worldwide business in gyro compasses for ships, and the Navy was very uncomfortable with Japanese naval personnel coming through the Sperry factories. Whereas the Ford Instrument Company never, until after the Second World War, never had any other customer other than the Bureau of Ordnance, which is why most people have never heard of it. So Norden, the Sperry had a bomb sight as well, and bomb sights and anti-aircraft computers are more or less the same thing, and the Norden bomb sight interfaced with the Sperry autopilot, which is one of the innovations that it had, in that the bombardier was actually flying the plane. But as far as I know, I haven't done a lot of work on Norden. There's one good book about it, but it was not an MIT-connected technology. Anybody want to guess?
Riding boats flying around first around the world.
Nope.
He wasn't? He wasn't.
He wasn't?
No, U.S. Army in 24.
Ah, yeah. But Post was the first solo around the world flight. It was that there's a Ford integrator in the space shuttle system. At least I hope there isn't one.
I thought it was that you boat was published by John Hopkins.
Thank you again.
Yeah, thank you.